you. All right, you guys, so today, what we want to talk about is a thing called polar coordinates, okay? Polar points or polar coordinates, right? Now, what is a polar point? You are going to have some point P, which has an R and a theta, where the R is the radius and the theta is the angle, okay? So we're going to graph points. Now, what you notice on this is kind of weird graph paper, isn't it? This is not normal graph paper. This is a polar graph paper. And then with polar graph paper, it makes it pretty easy. So point A would be a radius of 3 at pi force. So I find pi force is like right in here, right? That's got to be about pi force, right? And I like to go by half, so I like to make that 1, 2, 3, 4. So I go by halves on my scale. So I just go, 1, 2, 3, and there's point A, right about there. We just went to pi force, right, 45 degrees, and I just went out, 1, 2, 3. That's what my point is. Point B has a negative pi force. Well, okay, negative pi force we know is right about down here, right, negative pi force. We know that from the unit circle. That's about negative pi force, right? And I go 4. So I'm going to go, 1, 2, 3, 4. And here's point B. It's not that hard. Now with a negative radius, it's kind of weird because radii is really supposed to be positive, not negative. You can't really have it. But it's just a directional thing. So instead of going out 5, we're going to go directly opposite into 180 degrees. We're going to go back 5. So let's go to pi 6, which is here. And we'd go 1, 2, 3, 4, 5, except for negative 5, we're just going to go directly the opposite. So it's sort of like a push and a pull, right? So instead of going 1, 2, 3, 4, 5, we go backwards. For a negative radius, we're going to go backwards 1, 2, 3, 4, 5, and that's point C. Yeah, so it's the same thing, exactly. So you don't need to. You can, Ryan. You don't need to, and most of the time we wouldn't. So a great example. You're setting us up for example 2, aren't you? Look at you. You're setting us up. So give 2 other coordinates for the point 2 and pi thirds. So 2 and pi thirds. I'm going to mark that in a different color. Okay. So if I go 1, 2, here's my point. A couple of ways to describe that. Okay. One of the ways we can describe that is, you ready, Ryan? We could say it's going to be a negative 2 comma 4 pi thirds. We could. We probably wouldn't, but we could, because instead of going, to 4 pi thirds, we'd go, instead of going this way, we'd go backwards, put us right back to there, right? We could also spin it all the way around the circle, right? Same coordinate. We could say, well, we could call it a 2 comma and 2 pi plus pi thirds, right? Be a 2 and a third pi. That's one way to describe it. Okay, if we need another point, right? And then, so we've got 2 other. We could do a negative angle, or we could spin it all the way around. That's just the exact same spot, but just a different way to describe it, okay? Now, we need some conversions. So if I take a look, and first of all, let's graph this real quick. Graph and convert this into rectangular form. So I'm going to do a real quick graph. I'll do a little mini circle here. 2 pi thirds is about here, and I'd have 4, 1, 2, 3, 4. Okay, I meant to add these graphs and I forgot. It's okay. Okay, so there it is. This is 4. And my angle's 2 pi thirds. Let's call that point P. Everybody okay with that point? Okay. So I'll scoot it up so you can see a little bit better. Can you guys see it in the back? See the back? So how did I graph this? 2 pi thirds, we know from the unit circle. It's right about there. 120 degrees, right? And then a radius of 1, 2, 3, 4. Okay. Now, if I were to put this on a piece of graph paper, right, then how would it look? Well, regular graph paper, because we want to go ahead and put a rectangular form. The rectangular form is basic x y plane, okay? Rectangular form, xy, okay? So that means graph paper, okay? So if I were to take this point, it's going to be over here somewhere, and it should have some x and y value, right? Easy conversion. Make sure you write this down with the conversion from polar to rectangular. Here's our conversion. Very easy. We need an x and a y, right? We've got, in this case, an r and a theta. What we need is a x and y, okay? X is equal to simply r cosine of theta. And we can go back to right triangle trig and you go, oh yeah, that makes sense. We go back to the unit circle and realize the unit circle, it says that the x value is equal to what? That x is equal to the cosine, right? And then the y is equal to the r sine of theta, okay? So let's convert this point for 2 pi thirds into rectangular form. Well, that's not going to be too bad. We're going to go, then x is equal to r, which is 4, the radius is 4, cosine of our angle, which is 2 pi thirds, okay? That'll change this point's value. We'll get an x value, and then we can do the same thing with the y. I'll go 4 sine of 2 pi thirds. I'm going to highlight this. I'm going to put a big old box around here because that's my conversion. If we had done our reading, Colby, we would have had that in our reading and our conversion. That's okay. There it is, right? There's notes. Okay. So there's our conversion. Make sure that's in your notes, right? So how do you convert from polar to rectangular? It's super easy. X value is always r cosine of theta. Y value is just equal to r sine of theta. Well, let's go to the unit circle. What is the cosine of 2 pi thirds? Cosine of 2 pi thirds is a negative 1/2. So we're going to have a 4 times a negative 1/2, which is a negative 2. All right? For what is the sine value of 2 pi thirds? It's going to be a square root of 3 over 2. So we're going to end up with 2 square roots of 3. So as an x value, this x value here is going to be, coordinate of this is going to be simply negative 2 comma 2 square roots of 3. Same point, same location. Same point, same location. One is in a over and up. In fact, we're going to go negative 2, 1, 2. We're going to go up. What is the value of 2 square roots of 3? I don't know. 2 square roots of 3. About 3.46. So I'm going to have about a negative 2 and about a 3.46. So if I graphed it, I go 1, 2, 1, 2, 3.46. It's right about there, okay? Same point, same location. One describes it as a radius and an angle, a length and an angle. The other describes it as over and up. Does that make sense? Same exact point, same exact location. One describes it as a radius and angle. The other describes it as a back and up. Thumbs up? Capiche?
Yep.
Okay. Not that hard, is it? Okay, now turn the page. Now, example 4. We are going to come to Devin's question. Okay, so if I graph the point negative 3, 1, 2, 3, and 5, 1, 2, 3, 4, 5. We get a point right about there, don't we? Okay. Now, if we want to change that to polar form, we need to go ahead and change this into some r radius and some theta. All right. Well, what I would suggest is you make a right triangle out of it. This is what I would suggest. What the heck? I mean, it seems like a right triangle might make this easier for me. Okay, so if I make a little right triangle here. Okay, you guys see my little right triangle, right? What I really need is this length here. Let's call it r. Okay, that was quick.
That's hard.
That's right. I'll help you with it later. Okay. With retake, right? So what do you think? How can we find this length r? What do you think?
Formula.
Yeah, what formula do you think we should use?
Pythagorean.
Yeah, in fact, let's change Pythagoras' theorem into this. X squared plus y squared equals r squared. Isn't that basically a squared plus b squared equals c squared, but instead we're dealing with x's and y's. Now, Devin, when we square the negative, we get a positive anyway, don't we? Right? So, in this case, we're going to go negative 3 squared plus 5 squared equals r squared, right? We're going to get a 9 plus a 25 equals r squared. We already said r was the square root of 34, right? Hey, I think we got a formula up here, don't we? Let's go ahead and circle that formula. I think that's a formula we're going to need. X squared plus y squared equals r squared. Okay? And then, what we need then is an angle, all right? So finding theta. How do we find theta?
Very carefully.
I'm going to use the tangent inverse. I'm going to use the tangent inverse of my y value over my y. I said y and I wrote x. Y value. My pencil's exploding. It's all good. My y value over my x value. But then I'm going to have to figure out a reference angle. Okay, so then I'm going to need to find a reference angle, right? So, let me put my pencil back. So let's do our tangent inverse of 5 over negative 3, okay? And I'm going to, Devin, I'm going to ignore the negative, okay? Does that make sense? But I think you can see it visually that, you know, you don't really need to worry about the negative. You just need that angle, right? So, put this pencil back together. Let's go. Tangent inverse of my 5 over my 3. I'm not going to bother with the negative because I'm just going to get a negative angle. So when I find the angle, I'm really finding this angle. I'm going to go ahead and make my triangle. And we did this in our warm-up, right? We went tan inverse of, and if we do it in terms of degrees instead of radians, it doesn't matter. I'm doing it in degrees right now because it's easier to understand. Tan inverse of my 5 divided by 3. And I get an angle about 59 degrees. So that means that theta is 59, but that, we all know that that is this angle here.
We don't want that.
We don't, what we really want is this angle here, because we need it from the 0, right? And so to get that angle there, what we really want is this theta, which is 180 degrees minus my 59 degrees, okay? So then, 180 minus 59, 121, so theta is 121. So as a point, remember this is a point, we're going to go and change it to r theta. So our answer has to be a point, but in polar form, it's going to be r, which is the square root of 34, theta, which is 121 degrees. Eventually, we're going to put it in radians, yeah. Yeah, eventually we're going to need it in radians. The book is going to probably ask for it in radians. Every time I teach this, I always think it's easier to show degrees because we're so familiar with degrees, right? We're very familiar with degrees. So if I tell you this is a 59 degree angle, then I think you guys totally get that that's 120. If I did this in radians as a decimal,
9,000 divided by 6,047 pi.
there you go. All right. Okay, now convert x squared equals 4y into a polar equation, okay? Can this be graphed, right? So x squared equals 4y. So how do we convert it? Well, we've got to have a couple of things that we know. First of all, let's go back to something I might have on the other side. I got a couple of equations that describe x and y, right? From rectangular to polar. So I'm going to write that down. I know this, that x is equal to r cosine theta, and y is equal to r sine of theta, right? I'm going to substitute, right? So let me make a substitution. Let's put this in for x. Let's put this in for y, okay? So instead of x squared, I can write what x is, because I want to convert in polar. So polar is going to have, this is x and y, so that's rectangle. rectangular. X and Y is like graphing, like regular graphing, okay? This is a parabola. We could graph it, but this is a parabola. But anyway, that's in X, Y's. We want to get it into thetas and R's because that's what polar is. Polar's R's and thetas, right? So if I make a substitution, instead of X squared, I'm going to have a R cosine theta squared equals 4, and I'll do my substitution, R sine of theta, okay? That's correct, but it'd be kind of hard to graph it. But, you know, I can change some things around here. That'd be an R squared cosine squared theta equals a 4R sine theta, okay? Now, can this be graphed? Let's really mess some kids up. You want to mess some kids up?
Yeah.
You ready? Go to mode. Go to mode. We're in function, but we can graph pole. What do you think pole means? Polar.
Aren't those the little stars you did at the beginning?
Yeah, those little flowers. Yeah. Told you we'd come back to them. So let's go to polar mode. Okay. So went to polar. Everybody see what I did? My calculator went to polar mode. And then if I go to y equals, right? It's no longer y equals, r equals, right? Well, there's one in there, just for fun. I better check my window, though. My window, I'm in radians. Better change back to radian mode, though. I'm in radian mode, which is okay. So let me graph this. We talked about graphing these a long time ago. I showed you this, so let's graph it. Oh, my goodness. All right, I'm going to have to fix my window. Oh, my mode. Radian. Here we go. Now let me graph it. There you go. Now, first of all, is that a function? Come on, is that a function? No. You know, why is it not a function? It's not going to pass vertical line test, right? So what's really cool is that we can graph things like this. You can't graph things like this in regular functions. You can't. So how about this one? The problem is that to graph this one, you got to have r solved by itself. Okay, it's got to be r equals put in the calculus. So if I'm going to solve this for r, how would I solve for r? How about if I divide by r, they give me an r cosine squared theta equals a 4 sine theta, right? Divide by cosine, and I have r equals 4 sine theta divided by a cosine squared theta. We've been doing this stuff. I might write that as r equals a tangent theta over a cosine theta. Now, where did the tangent come from?
Sine over cosine equals theta.
Now, let's see if I can graph this. I might be able to graph this and see what it looks like, okay?
Wait, but where'd the 4 go?
Yeah, where's the 4?
It's right there. Didn't you see it?
Yeah. It's in invisible ink.
It is. So let's see if I can graph this. See what this looks like. So if I go 4 tangent theta, I'll clear the whole thing. 4 tangent theta. If I push my X button, guess what pops up? Theta, right? If I push my button here, I get theta, right? This time, because my calculator knows I'm in polar mode, divided by cosine theta. Let me graph it. Hey! Didn't I tell you it was a parabola?
Zoom out a little bit.
Didn't I tell you it was a parabola? It is. I knew it was a parabola from way back there. Okay? Crazy. You can. I'm going to keep going, okay? You can, yeah. What happens is this. Okay, if I clear this.
Does it make like a leaf shape?
You ready? Watch it carefully, okay? I can't do this in slow-mo, okay? Watch carefully. Graphs that half, then comes down, graphs this half. Yeah. Well, no, it doesn't come back around. It just graphs from 0 to 360. And from 0 to 180 is here. And then from 181 to, yeah. Okay, now, 6. Let's go the other way. Let's express the polar equations into rectangular equations. So before I do anything, now I want to go ahead and I want to go back and change things to x, y's, okay? I want to have some y equals, not r. So how do I do that? Well, let's go back to what we know. So there's a couple of things I have as far as identities. Let me circle what identities I have, right? I've got this one here, and I've got this one here, okay? So I know that secant, before I do a whole lot, r is equal to 5 divided by cosine theta. You all right with that? Well, that was an easy move. If I take both of these, I could say that cosine theta is equal to x over r, and I could say that sine theta is equal to y over r. I might highlight and circle that as kind of like a little identity. Okay, I want to hang on to that too, okay? Because how's that going to help me? I can make a substitution now, okay? All right. So if I want to change the cosine, I can rewrite that as an x over r, right? If I want to change my r into x and y, so I'm going to go up to this form here, okay? So another form I might want to write is that r is equal to the square root of x squared plus y squared, okay? Might highlight that too as one of my little identities. Highlight that as one of my little identities. See how that's going to help me, okay? So now let's go ahead and see what I've got. So what I could do is instead of writing r, let's write x's and y. So this r I'm going to rewrite as the square root of x squared plus y squared equals 5 over, let's see, cosine. Cosine theta is x over r, right? And I still have an r. Doggone it. I'm still stuck with an r.
Wait, are you trying to get rid of the r?
Yeah, so what I'm going to do to get rid of the r is plug that one back in there, okay? Alright. Now, there might have been an easier way to do this. I always do things the hard way. Can I back up and do it an easier way?
No.
Sure. I'm going to back up and do it an easier way.
No.
I'm doing it the hard way once again. Alright, I'm going to back up. I'll back up. This will work. Stay awake, Luke. Don't fall asleep on me yet. R equals 5 divided by cosine is x. Cosine is going to be the x over r. Okay. This is much easier. Let's do it the hard way. Flip my fraction. Okay, let's flip my fraction. R is equal to 5r over 5 over x. If I multiply by x and divide by r, what happens? Multiply by x, divide by r, I'll have x equals 5. What kind of graph is that? It is linear, but it's also straight up and down, right? X, it's vertical. So let me see. Hold on real quickly. I'm just curious. Let's see if I graph the original. 5 divided by cosine theta, right? So I'm saying that these are the same graph. Wow, there it is. Okay. B. R equals 2 sine of theta. So, again, what is sine equal to? Sine could be equal to my y over my r. So I've got r equals 2 times my y over my r, right?
Right.
Multiply by r, what do you get? Hi girls, what's up? No. Thank you. Are you guys done? Nice. Was it easy? Good. She's the smart one in the class. She really is.
The tall one?
The tall one.
That's us right here.
Yeah. Multiply by r, I get an r squared equals 2y, right? Now what is r? I got to get x and y's. What's r squared equal to? R squared is equal to, yeah, isn't it? Okay, so replace this to x squared plus y squared equals 2y, all right? That looks like it could be almost a circle, huh?
Can we graph circles?
Yeah, let's check it out. Let's see. Let's graph this thing. So, Let's see what happens. Well, that's my answer, by the way. All right.
That's your answer.
That is my answer. Crazy. 2 sine theta graph. It is a circle.
I don't know if we call that a circle.
That doesn't. That's like a little tiny circle.
Well,
Might be like a big
let me
circle.
change my window, okay? Change my window. We'll go from -3 to 3 and
No.
-3 to 3. Okay, ready now, graphic. How's that?
Oval.
It's an oval.
It's not oval. It's not an oval or an ellipse because, okay,
Not a circle, I'll tell you that.
we're going into your world. Your world. This film has not been formatted to fit the screen. Remember that scene, that warning when you guys rent a movie? Sometimes it's because when the movies make a picture, they are putting on a big rectangular screen, right? When you come back home, well, back in the old days, old days, you'd have a square TV. Now everybody's got a big flat screen TV that's rectangular, right?
Right.
Yeah, welcome to America, right? Anyway, the same thing's going on. This is a square, this is a rectangular screen. But now there is a button if you really want to make it square. You go to zoom, square. So like in the old days, they would format, they'd format the movies to fit the screen, right? Well, this is how we can do it.
It's a donut.
Wait, what'd you do?
I went to zoom and I went to square. So I squared up my screen. Okay. And
But
that's
does that change? Like, doesn't that